So, wire X has current in it, which is 65 amperes, as shown in the figure, and wire Y, which is connected to another circuit, is free to move vertically and is suspended at rest by the magnetic force between the two wires. Well, let's just analyze this part for a second, right? So they did not say that gravitational forces are to be neglected. That means that wire Y is getting pulled down by the gravitational force. Yet it is suspended at rest, meaning that the magnetic force is pulling it up, and the magnetic force is equal to the gravitational force. Now, how would wire Y be attracted to wire X? By having the same direction of current. So the rule says if you have two wires with current running through both of them, if the current in both of them is running in the same direction, the wires will attract each other, which will explain why wire Y is being pulled toward wire X. That's because wire Y also has current in it that's running in the same direction as wire X. A says, calculate the magnitude of the magnetic field produced by wire X at the position of wire Y. You should know that the equation for the magnetic field caused by a wire is equal to mu I over 2 pi r. Mu is 4 pi times 10 to the power of negative 7, and I is the current of wire X, which is 65 amperes. 2 pi r, r being the distance between them, which is 0.025. Let's see how much that is. And I got myself 5.2 times 10 to the power of negative 4 Tesla. BI, calculate the magnitude of the current in wire Y. Now, like we said, wire Y is feeling a magnetic force on it due to wire X. And now we can equalize the magnetic force on wire Y to the gravitational force on wire Y. So we're going to say ILB is equal to mg. So I is equal to mg over lb. So m over l times g over b. Why would I separate them? Because I know that mass per length is given to me as 5.6 times 10 to the power of negative 3. So here we're going to have 5.6 times 10 to the power of negative 3. G is 10, and B is the field that we found in part A, which was 5.2 times 10 to the power of negative 4. So let's do the math. And I got myself 108 ampere. All right, indicate the direction of the current wire Y. As we said, wire Y is being pulled toward wire X. That means whatever direction of current is in wire X must be the same exact direction of current in wire Y, which means going to the right. Okay. Now wire Y is moved to a new position that's going to be closer to wire X, but still wire Y is going to be closer, lower than wire X. That means that we're going to be moving wire Y to here, let's say. So it's going to be closer to wire X, but still below wire X physically. Now you're going to be releasing wire Y from rest, and you're going to talk about the initial motion of wire Y with justifying our answer. So look, as the distance between the two wires is reduced, it is right, because they were initially at 0.025, now they're going to be closer than before. The magnetic field is inverse with R, so the B will increase. So Fm is equal to ILB, so Fm will also increase. So Fm will be bigger than Fg, so the wire will accelerate upward. Okay, D. Suppose wire Y is now moved to a position of 0.025 above wire X. That means that this is the new drawing. This is wire X and this is wire Y. And now they are how far apart? 0.025 meters. What changes in current, if any, must occur to maintain equilibrium? Well, look, wire Y is still feeling the gravitational force pulling it downward. And to maintain equilibrium, that means it has to be getting pushed up by the magnetic force. That means that wire X has to be repelling wire Y. Okay, so that means that wire X must now repel wire Y to push it up against gravity. So now Fm would still be equal to Fg. Now, for one wire to repel another wire, the currents in them have to be going in the opposite directions. That means if the current in wire X was going to the right, the current in wire Y has to be going to the left. So the direction of current in wire Y must now be reversed. Okay. With wire Y still above wire X, the circuit is connected to wire Y is now removed. So now wire Y will have no more current in it from a circuit. Okay. It's how long? 1.2 meters long. It's moved vertically up away from wire X at the velocity of 3. EI, find the magnitude of the induced EMF in wire Y when the wires are 0.050 meters apart. Okay, let's just clear this up. So essentially, the equation for the induced EMF, you should know from your reference sheet, is going to be B L V, V being the speed, and B being the magnetic field. Okay, so what is the magnetic field? Let's find that first. So we're going to do mu I, just like before, 2 pi r. So 4 pi times 10 to the power of -7. The same I as before, which was 65 amperes in wire X. 2 pi with a new distance now being 0.050. Let's see how much that is. Now I got myself 2.6 times 10 to the power of -4 Tesla. Okay, we're going to plug that back in the B. So 2.6 times 10 to the power of -4. The length is 1.2 and the speed is 3. Let's see how much that is. So I'm going to be getting 9.36 times 10 to the power of -4 volt. Okay. Double I, indicate which end of wire Y is at the higher electric potential. Now look, wire Y is going to be experiencing a magnetic force on it due to wire X. The current in wire X is going to the right. So right now I want you to use your right hand rule, and I want you to point your thumb to the right. And I want you, as you do that, your fingers will be curled to be below, so to be going into the page below wire X, but to be going out of the page above wire X. Okay? Now, wire X is being moved vertically upward. So we're going to, wire Y is going to be moved vertically upward. So I want you to use your right hand rule again, with now the thumb for wire Y to be going up and the field to be going out of the page, which would be your fingertips. So now point your thumb up, point your fingertips out of the page. You're going to have to curl your right hand so that the palm is pointing to the right side. So the palm will point to the right side. The palm is the same as the magnetic force. And this will cause the charges to basically get pushed, the positive charges to get pushed to the right side. Okay? And that means you're going to have more positive charges on the right side than on the left side. And that means you're going to have a higher electric potential on the right end. Okay? So yeah. So basically, the magnetic force on wire Y, due to its movement in the field, in the magnetic field, by wire X, will cause the charges, the positive charges, to move to the right end. So this end will have the higher electric potential.